Welcome! In the previous video, we looked at the different types of DA converters and how the DA converter of this STM32F446ZE microcontroller works.
In theory.
Right. Now it's time for practice.
That's right. In the following, we will try to produce a fixed output voltage and also a fixed frequency sine wave using the DAC. Let's start with the first task, setting a fixed output voltage. In this exercise, the signal generated by the DAC will be measured using a multimeter on the PA4 leg of the microcontroller. Let's get to the programming. We've already created a blank project to save time. You already know that from chapter 4. This is a plain, completely empty project for the STM32F446ZE microcontroller. Nothing has been configured yet. Let's set up the DAC peripheral first. To do this, after opening the project, click on the .ioc file in the Project Explorer, which contains the configurations. In the graphical interface that opens, you can easily set the PA4 leg to DAC out 1 output. Other settings for the DAC are also the easiest to adjust in the interface shown in the picture. In the Categories tab, click on the DAC in the Analog section to see the default configuration. We will leave this untouched for now, but we will come back to it in the next exercise. When saving the .ioc file, the development environment may offer to automatically generate the structure and function needed to set the DAC control register, but if it does not do this, we will have to manually generate the code. You will find these elements in main.c in case you have not checked the option to generate the functions for the peripheral in separate files, and you will also write your own program here. To open main.c, navigate to Core in the Project Explorer menu on the left, and then to the src directory within it. In main.c, this HDAC structure of type DAC handle type def is responsible for handling the DAC. The settings are written to the control register by the mxDAC-init initialization function. In the simplest implementation, we are only a few lines of code away from our first successful digital to analog conversion. Let's find the user code, begin toLine in the main function.
The meaning of this line is that this is where the user code starts. And it is important to write your own code after it, because if you change the .ioc file and rebuild the code according to the new settings, the development environment will delete the code fragments in the non-user code area.
Indeed, this is very important. And here we write the following. Let's create a float variable with the name uOutput. Its value should be 1.0 because we want to see 1 volt at the output. Then, let's create an unsigned 32-bit integer. Its name should be dinput. This value will be sent to the input of the DAC. dinput equals uOutput multiplied by 4095 divided by 3.3. And then we cast all this to an unsigned 32-bit integer. Then call the HAL DAC setValue function with the HDAC structure as the first argument. Second argument is the DAC channel 1 macro because we want to set this value for the first channel. The third argument is DAC align 1 to BR because we want to align the 12-bit number to the right. The fourth argument is the dinput. After that, call the HAL DAC start function, the first argument of which is HDAC in the same way, and the second is the DAC channel 1 macro in the same way. After building and uploading the code, a voltage of 1 volt will be measured between the PA4 leg of the microcontroller and the GND. We will check this. Gerge, please measure the PA4 leg and I will switch on the multimeter. And you can see that
1 volt is measured.
That's right, we will measure 1 volt, so our circuit and our code are working. That's great. And now we can move on to our second practical example.
Only if you have tried this example, of course. If not, stop the video here and try it yourself.
The second task is to generate a sine wave. In this exercise, a sine wave of 100 points is calculated with the microcontroller, and the output analog signal is generated from this using two methods. In this exercise, we want the frequency of the sine signal to be 10 Hz. Two solutions are presented. In the first case, we use the main loop of our program to adjust the output point by point in the same way as in the previous task. In this case, the array of digital values of the sine signal is traversed using a loop. Since the period of the sine signal consists of 100 points, we must cycle through the array 10 times per second, so we must change the output value 1000 times per second. This is achieved by setting a delay of 1 millisecond after this output is set. Now, let's see the code and continue the previous project. To the private includes part, we add math.age, which we will need for the sine calculation. In the user code section, add the function to calculate the sine wave points. The input of the function is the pointer and the length of the array to store the data. So, void generate sine, and in the argument list uint 32t asterisk sine and uint 32t length. Then, we start a for loop from 0 to length, and here we calculate each point of the sine wave. So the ith element of sine equals the sine of I multiplied by 2 times pi divided by length plus 1 times 4095 divided by 2. Let's have a closer look at this line to make sure everything is clear. The elements in the argument of the sine function, so the I multiplied by 2 times pi divided by length, are used to divide the interval from 0 to 2 pi into exact length pieces, and finally calculate the value of the sine function in each of them. Then, we add plus 1, because the sine function takes a value between -1 and +1. But our DA converter can only produce a positive voltage in this case, so we add 1 to the whole function. So the result is between 0 and +2. However, this is not quite right either, because if we multiply +2 by 4095, which is the maximum value on the 12-bit DA converter, 2 on the 12th minus 1, we would get a too large number which the DA converter could not produce. So let's divide it by 2, and you'll see this a little later in the line. In the next step, call the function you wrote in the appropriate place. To do this, initialize a uinit 32t array with 100 elements and the name of sine data. After that, call the generate sine function and pass it to the array you just created and the number 100, since the length of the array is 100. Finally, in the main loop, type the following lines to set the analog output. So we are in the while loop and start a for loop. I equals 0, I is less than 100, I ++. Then set the digital input with the HAL-DAC set value function. The first parameter will be the HDAC structure, followed by the DAC channel 1 macro, then the DAC align 12BR macro, and the fourth argument will be the current element of the array. We have already seen this in the previous example. Then call the HAL-DAC start function with the same arguments as before. This triggers the analog to digital conversion. Then the HAL delay 0 is called.
Delay 0? We will wait 0 milliseconds?
Yes, exactly. HAL delay 0.
But does it make any sense?
Yes, it's good that you asked that because there's a twist. We will wait 1 millisecond, but still write 0. To find out why this is the case, we need to understand the operation of the HAL_delay function. Until then, please compile the program and upload it to the controller. So the time base for HAL delay in this case is provided by systick. The systick is a timer inside the processor core which in this project generates an interrupt every 1 millisecond. And in the interrupt handler, we increment a counter. What HAL delay does is that when it is called, it reads the value of this counter and then waits until the value of this counter is incremented by n, where n is the number that was specified in the function argument. There is a potential issue when calling HAL delay 1. When you call the function, the counter value may change immediately after the call. As a result, you might end up waiting for almost no time and the function will continue executing because the counter has incremented. This behavior is not what you would expect, since the HAL delay function is supposed to wait for at least the specified time in its argument. To address this, HAL delay adds 1 to the argument. For example, if you request a delay of 1 millisecond, the function will actually wait for 2 milliseconds. If you input 0 milliseconds as the argument, the function will wait for 1 millisecond instead. This design ensures that the waiting period fulfills the minimum expected time. We don't use HAL delay in the 1 to 2 millisecond range because it works with a resolution of 1 millisecond, so we'll show you a much better solution in the next chapter. Now, back to the test. Gergő, how are we doing?
I'm done. The program is running and the oscilloscope has been connected to GND and the PA4 leg of the microcontroller.
And we can see here on the display that the 10 Hz sine wave has appeared, so our project is working. Excellent!
This is great, but what happens if we want to implement other features in the project? Wouldn't timing be a problem?
Yes, the thing is that this is a real problem. And if we put in extra parts, then the 1 millisecond wait would most certainly be violated. We need another method for that.
Do you mean a DMA solution?
Exactly. In the next part, we'll do a DMA version of this project, which will be much cooler than this one. So stay tuned. We'll see you there. Bye!
See you!